Now that we've learned the basics of encryption, let's talk about a related concept, hashing. We've already talked about encryption. Encryption is used to scramble data, and a defining characteristic is that once it's been scrambled, it can be unscrambled as long as the correct key is provided. Hashes are also used to scramble data, but the main difference is that the data can't be unscrambled no matter what. Now, you're probably wondering why we might want to turn our data into irreversible gibberish. Well, when you think of a hash, you should think of a fingerprint. Now, there's an urban legend that says that no two people can have the same fingerprint. That's actually not true, but it is very unlikely. So, a hash is a lot like a fingerprint. There are hashing algorithms that use keys, like we saw with encryption, and there are hashing algorithms that don't use keys. In this section, we'll focus on the ones that don't use keys. So, with these hashing algorithms, we supply some input data and no key. The algorithm spits out a fingerprint. If you run the same data through the algorithm a second time, you will get this same fingerprint. If you run the data through the algorithm a third time, you will again get the same fingerprint. If you modify the input, even just by changing one letter or even just one bit, the hashing algorithm will spit out a completely different fingerprint. So, the idea is that two different inputs will not produce the same fingerprint or output. Now, it turns out that that's not actually true. Just like it's possible for two people to have the same fingerprint, it's also possible for two different inputs to a hashing algorithm to have the same fingerprint. It's just very, very unlikely. One reason we use hashing is to detect whether data wasn't transferred correctly or was otherwise messed up somehow. Let's say that we create a computer program and publish it on our website. We could also run our computer program through a hashing algorithm, like, say, SHA-256, and publish the resulting fingerprint on our web page. Now, when someone downloads the program, they can use the SHA-256 hashing algorithm to compute a fingerprint for the copy that they downloaded. If they get the same fingerprint as the one that we published, then they know that the data was transferred without getting messed up or corrupted. We also use hashes to detect tampering. For instance, if someone downloaded our program, ran it through the SHA-256 algorithm, and found that the hash didn't match, it could be because someone hacked our web page and tampered with our program. Maybe they modified it so it did something bad. Incidentally, we call such a program a Trojan, named after the famous story of the Trojan horse. But if someone hacked our web page and modified our program, they could have just computed the hash for the modified version of the program and replaced our original fingerprint with the new one. Then, no one who downloaded the Trojan program would notice anything suspicious. I'll explain how we deal with that problem in a little bit. The hashing algorithms that we'll talk about in this section do not use a key. They just take input, usually referred to as a message, and spit out a sort of fingerprint value. There are some other hashing algorithms that use a key, and we'll talk about those later. So, I said that you can't unscramble the output from a hashing algorithm. Why is that? Well, it turns out that hashing algorithms lose information during this scrambling process. Since information is lost, there's no way to unscramble the data. Some of the necessary information has gone missing. See, these hashing algorithms always give you the same amount of data as output. regardless of how much data you provided as input. For example, the MD5 hashing algorithm always produces 128 bits, or 16 bytes, of output. Once it gets encoded for human-readable output, it's shown as a 32-byte, or 32-character, string. It doesn't matter whether we give MD5 1 bit or 100 terabytes of input. It will always produce 16 bits of output. So clearly, some or a lot of information gets lost in the process. And that's why you can't unscramble the output of a hashing algorithm. Now, sometimes you'll hear the terms hash algorithm, hashing algorithm, hash function, or even hashing function used. They basically all mean the same thing. Furthermore, we sometimes use the term hash to refer to both the algorithm and the output that it generates. Sorry if that seems confusing, but that's just how it is. So, there are 4 key traits that make a hashing algorithm good. First, it should be easy to compute the fingerprint or hash value. In other words, it shouldn't take a computer 5 minutes to run the algorithm. Next, it should be essentially impossible to unscramble the data. That's usually a pretty easy target since hashing algorithms lose information along the way. Next, 2 messages that differ only by 1 bit should produce completely different hashes. And last, it should be very, very, very unlikely for 2 different inputs to result in the same hash value. The more unlikely that is, the better. Here are some example hashes. If we run the text hello through the MD5 algorithm, we get the output shown at the top. If we change just one letter in the input, say changing an L to a K, we get a completely different hash as shown in the second example. The same is true for other hashing algorithms such as SHA-256. You can see in these examples that MD5 always produces the same length of output, and SHA-256 also always produces the same length of output, regardless of the size of the input. One of the security issues with hashing algorithms is that 2 different inputs could produce the same fingerprint. Remember, this is very, very unlikely, but not impossible. When there are 2 or more different inputs that result in the same hash value, we call this a collision. This is like 2 people having the same fingerprint. Older hashing algorithms usually produce shorter hash values. For example, MD5, which is fairly old now, produces 16 bits of output. SHA-256, which is much newer, produces 256 bits of output. The length of the output alone helps reduce the likelihood of these collisions. It's also the case that hashing algorithms, like encryption algorithms, can have mathematical or code level flaws that introduce weaknesses. Furthermore, the faster a computer can compute a hash, the faster it can try to guess the input that created a specific hash. We'll talk more about that later. Older hashing algorithms like MD5 have already been demonstrated to have collision problems. In some cases, an attacker can purposely cause 2 inputs to have the same output. That's still pretty unlikely, but it definitely can be done. That fact makes MD5 essentially unfit for use in new web applications and really means that it should be phased out of older applications. These days, we usually recommend newer algorithms that produce more output, like SHA-256 and SHA-512. Unfortunately, even the newest algorithms can be cracked with enough computing time. I'll talk more about the time it takes to crack a hash a little later. For now, let's focus on how attackers try to crack hashes. I mentioned collision attacks earlier, where an attacker can force different inputs to have the same output. Those attacks are used in certain scenarios that I'm not going to discuss much, if at all. Frankly, the only pragmatic solution that we can use to protect against those types of attacks is to use newer, stronger algorithms. For now, we'll focus on a couple of more common attacks. These attacks are important because many web applications use hashing algorithms to store passwords. I'll talk more about exactly how that's implemented a little later today. At a high level, a website might ask you to set a password. Instead of storing your password in the database in plain text, they run it through a hashing algorithm and they store only the hash. So they have no record of your actual password, and your password can't be reversed from the hash because you can't unscramble a hash. Sounds good, right? Well, let's say that an attacker uses a SQL injection vulnerability to get all of the password hashes from the database. It turns out that there are a couple of attacks that the attacker can use to figure out the original password from the hash. The first one is called a brute force attack. Basically, the attacker uses a computer program to generate hashes for all possible inputs and compares each one to the hash they got from the database. They would basically generate a hash for the letter A, then one for the letter B, one for the letter C, and so on. If one of those inputs produces a hash value that matches a hash they got from the database, they can look at what input they used to generate that hash. Then that's it. They know the password. It doesn't matter if it was the actual password that the user entered or if it happened to be a very rare collision. Either way, it will work to get into the website. Now, this takes a long time in most cases, but the process can be sped up through various techniques. The other common attack is closely related to the brute force attack. It's called a dictionary attack. It's like a brute force attack, but rather than computing the hash for every possible input, the attacker makes a list of strings that they think the password might be. So basically they make a bunch of guesses. Then they use a computer program to send each one of those strings through the hashing algorithm and check for outputs that match a hash they got from the website. Again, if they find two matching hashes, they can look at which guess produced that output, and they'll know the user's password. Here's what a dictionary attack looks like. It's literally just guessing at what the password is, running the guess through the hashing algorithm, and checking to see if the hash matches the one they got from the database. If it matches, they know what the password is.